precision. So we then, at the same year, were given money by the Department of Trade and Industry to purchase a second ME machine. So you could see that the 80s was a period of rapid expansion of more sophisticated tools. This continued into the 90s, where we purchased another more modern MOVP reactor. We converted the very first MR100, the first metal organic reactor, to try and grow these dilute nitrides, because we could see dilute nitride materials were becoming very important. And then, once we proved that we could handle those materials, we then went and got a new commercial Thomas-Swan reactor to grow the gallium nitride from the blue LEDs and blue lasers. So, since then, we've been sort of continuing to add on more tools, and in the early part of this decade, we got a third MBE machine, which is the slightly bigger version. I mean, it's hard to see the size of these things, but they sort of occupy a small lab quite comfortably, and the MBE3 and the MOVP5 started to take over doing a lot of the basic research. So all these things that I've described are the expansion from growing a single centimeter square of material to now growing maybe, with the latest MOVP reactors, we can grow 6 or 7 2-inch wafers at the same time. So it's a massive scale up in our capability. Now, you can ask the question, why is it at the university level are we then requiring this amount of material? Because the answer to that is actually people are starting to do more advanced things with the material, they're trying out more experiments, and a centimeter square is not very big at all. So if you've done one experiment on a piece and then you want to try that experiment out again a bit later on, you've used up all your material. So it's always useful to have more of the material for you to go and do your experiments with. In parallel with the development of the growth, but maybe starting slightly later, we started to develop the device processing, because you are producing the material, you're growing the material, you then also want to do things like to process them and to make actual devices, because the raw material in itself is of not much use. So we started to get things like scanning electron microscope to allow us to examine things in fine detail. We've got optical mask aligner, contact mask aligner, deposition systems, ellipsometers, annealers, and so on and so forth. And the tools are getting more complicated and bigger, and they allow you to process full 2-inch wafers at a time. So what you can see is that, here are some snapshots of some of these capabilities that we have. The point is, no one university can reasonably be expected to have that number of growth kits and this amount of processing equipment in a clean room and to run it for themselves. It's just too difficult. Most universities that have capabilities like this have maybe 1, maybe 2 growth kits and a small device processing lab. The problem is that that is not actually very economical to do, and it makes much more sense to scale up, because if you scale up, you have the economy of scale. And so this is what Sheffield has done. It scaled itself up, got central government funding in, and then it makes its facilities open to other people. And here is an example of some of the characterization data we have. We have optical, structural, electrical characterization equipment. So it's a very comprehensive facility that is available there. Now, once we were sort of set up by the time we were set up, we started to then advertise for people to come and use us. So the very first 2 grants we had were from the University of Bath and from the University of Cambridge in 1980. As I said, since then we've had many grants from most of the main research-intensive universities in the UK. So, the Cambridge, Glasgow, Imperial, UCL, Sheffield, of course, Surrey, and and so forth. Now, I think I've sort of done a reasonable introduction there on what the central facility is and what equipment we have. I think it's instructive to look at the cost of running the central facility and why the central facility model is a very good idea for anyone wanting to start research into a new area, especially in a developing country like Malaysia, where the resources for research is somewhat limited. The cost of a LPE growth reactor in 1979, about 30 years ago, was about £4,300. The cost of a MOVP reactor a few years ago just exceeded £1 million. Okay, so now the MOVP reactor is a much more sophisticated thing. It does much more, but unfortunately it costs a whopping 250 times more than what it cost us 30 years ago. So it's gone up much faster than inflation. Okay, so the cost of the clean rooms as well in 1979 was less than £1,000 per square meter. Now it's about £6,000 a square meter. The cost of wafers is also increasing because wafers are sizes in 3-5 semiconductors for a long time were around the 2-inch mark, but now very quickly people are starting to work on 4-inch indium phosphide. Gallium arsenide is touching 6-inch. Tolerances are getting tighter, and now there's more automation coming into play. So it's the same as what happened in silicon about 10, 20 years ago is now what's starting to happen to the 3-5 industry. So the technology is getting more mature. The main people working in this field are now large companies like Luminex, Philips, Agilent, Avago. And these people can afford to buy all these very expensive bits of equipment, which means that the manufacturers are only making very large bits of equipment, and the poor universities, when they try to buy these things, are finding that they can't afford to purchase any of these for their R&D activities. So, the cost of running a central facility for Sheffield in the last 4-year period, we are now coming to the end of the one of our roles, is about £1 million a year. Now, this covers the cost of the manpower that I described, 3 or 4 technicians, 3 or 4 research scientists, infrastructure for 4 years, and this is based on the estimated cost of the 4-year operation, and this is based on something like us producing something like 1,000 wafers per annum. This is not the full cost of doing the work. This gives us a baseline amount of funding. It's about 60% of our funding. Another 40%, another maybe 3 million or so, 2 to 3 million, will come as people start to use us, and they have to give us some money to actually use us. But because we've got this £4.5 million up front, the costs to the